Moving to the featured event on the role of emerging technologies and innovation. This session will be split into two simultaneous sessions. Featured event 1A on digital technologies will be chaired by Shri Kamal Kishore, member NDMA India. This session will be held here in this hall. Featured event 1B on engineering and nature-based solutions will be chaired by Professor Rajiv Shaw, Keio University. This session will be held at Aftab, the hall on the left outside the registration area. When we conclude this session, we will break for lunch and reassemble here at 1:45 for working session 2. I now request the chair and the speakers for the sub-session FE1B to proceed to the designated hall. Other participants may choose to attend the session that interests them. Featured event 1A here and featured event 1B at Aftab, which is left of the registration area, outside.
To the session, the featured event 1, which will talk about digital technologies. We have a very, very interesting panel here, which will be chaired by Mr. Sergei Kachanov from the Russian Federation. He is the head of the Research Institute on Disasters as part of EMERCOM. Unfortunately, because we do not have simultaneous translation, and he speaks Russian, and most of us don't. So in that case, I will assist him in the moderation, and our colleague from the Russian embassy will give him simultaneous translation, and he will make closing remarks towards the end. So that's how we are going to manage. This session has 5 speakers, really a stellar cast. We have experiences from IBM here in India, Bangalore. Stella Novo, who's been working on application of artificial intelligence for flood forecasting. We will look at how to use sensing technology, machine learning for in real time tracking the performance of infrastructure, how infrastructure assets are deteriorating. And we have Mr. Andre Cuomo from Sakaitis, he will talk about that. And then we'll have a presentation from SARMAP from Mr. Michael Anthony, and then Daisuke Abe from Weather News. So I would now request Seema Kumar to talk about the IBM's work in this space.
May I have the presentation on the console? Can't run the videos from there.
They were saying that it's all done from this system. It's now connected to the Wi-Fi.
Okay. So I think you'll have to skip the video and do it later. No worries. Okay. Okay, the technical panel starts with technical difficulties. Um, Very good afternoon, everyone, and it is my honor and privilege to be here representing IBM. I have been leading in the organization a series of initiatives, working with the ecosystem, working with software developers, working with startups, so on and so forth. And I've more recently moved on to also lead the cloud business initiatives for IBM in India. So I'm going to spend the first 5 to 6 minutes talking about a very unique program we launched last year in 2018 as a founding partner. This is the Call for Code global initiative. So looking at the various strengths that IBM as an organization brings to the table, and then thereby marrying the aspect of the strength of technology to being more relevant and giving back to society. Those are some of the basic principles that led us to even conceptualizing this program, and we had a very successful run in the first year of the program. So there's a lot already spoken in the conference here in the last 2 days in terms of the impact we face in terms of natural disasters, both in terms of human lives as well as a large financial impact. It is seen as one of the most high-reaching natural phenomenons, be it earthquakes, be it volcanoes, be it floods. We see it in every other country across the globe. So here there are some statistics out there which really show, like, for example, just if you look at the area of earthquakes, there are over 800,000 human lives that have been lost across the globe in 2010 alone. Similarly, you see storms causing massive damage, even closer home. That's something which we see not just in terms of life, but in terms of the massive reconstruction effort that it creates. So given that background, the first year of Call for Code was taken, we took the aspect of natural disasters as the area to solve, okay? And thereby looking at some of the greatest challenges and how technology can impact. Now you look at the other side of the spectrum, right? So software is changing the world. Everything is being rewritten in code across the globe. You have seismic shifts in terms of data, AI, cloud, blockchain, causing dramatic improvement in the way we work, the way we live, and the way we interact as consumers. A lot of this is possible because of the developers out there, the software developers, the technologists out there. We have over 22 million developers across the globe. India, incidentally, is the second largest nation after the United States. We have roughly around 4 million developers in this country. And all of them contribute directly to businesses globally, right? So you're building applications, you're building solutions relevant primarily to a business context where you're driving some of the largest banks, the largest telcos, so on and so forth. But then what if the developer per se, right, the profession of the developer, the talent and the skills that developers have can be put into solving some of the largest global problems? And that was the premise based on which the Call for Code program was created, where getting developers to give back to society using their skills by building solutions that matter, and looking at innovative ways of these technologies helping mitigate the losses that we incur during and after a natural disaster. So this was launched in 2018. We as IBM have invested over $30 million over a 5-year term. So this is an annual program. Last year, 2018 was the first year. We've already announced it for 2019. Where we work hand in hand with a series of partners, and I'll come to our key partners and organizations who are joining hands as we go ahead across the world encouraging developers to participate. What is in it for somebody who is working in an IT company or as a startup or a student? What do they get? They of course get hands-on skills, access to a lot of free technology on the cloud, as well as a grand prize. So the prizes that were given away last year were in the range of $200,000 to $20,000 that they took away as prizes. And then thereby it lives on, right? There is an opportunity for them to go and implement that solution in the areas where it matters most. So we have various affiliates and sponsors who are also part of it. So last year, we had over 100,000 developers participate, over 2,500 applications that were created. We ran a series of call for code days or hackathons where the developers were presented some use cases relevant, very contextual to their local scenario, and building teams and actually building solutions around that, and several supporters globally. In terms of the various organizations, so IBM is a founding partner for Call for Code. We've joined hands with David Clark Course, which is again an organization who supports various humanitarian causes across the globe. We also have the UN Human Rights Organization and American Red Cross, all as some of our primary partners. We have several other organizations supporting it as affiliates, as sponsors, and one of the key principles was open source. So all the solutions built were based on open technologies, and we had Linux Foundation helping these teams really take it to the next level, right? Because open source requires a certain process and a discipline to really make it real when you're going into the implementation space. So this is just a quick view of all the organizations that partnered with us last year. And incidentally, in India, we had one of the largest participating countries was from India. We had over 60% of the participants or the registrants were from developers in India across the organization. So, and then we look at the winning solutions, right? So this was a several month-long activity where developers came together, built these solutions, and we did a series of trainings and online sessions, as well as gave them a lot of reusable assets, open source assets or patterns that they could use. So in the area of IoT, for example, right, where you could use an IoT-based sensor or a device to transmit and communicate across multiple locations. Blockchain was another area. In the earlier session in the morning, we were talking about building trust and transparency into the system. So one of the areas where we saw a lot of solutions coming was when you're doing the disaster relief activity, how do you build in the transparency that all the donations or all the relief material is reaching the right agencies or the right beneficiaries in the system, and how do you use a technology such as blockchain to do that? The winning solution, incidentally, was a team of 4 developers who met online as a result of that challenge. It's known as Project OWL. I think I'm not able to play the video here because let me try. So what they built was an IoT-based solution where they created a mesh-based network, right? So one of the first things that happens when disaster strikes is you lose connectivity, right? Or you lose access to a mobile network or a Wi-Fi network. And how do you create, okay, so let me just play the video.
We were inspired by the whole hurricane situation in Puerto Rico. All communication was down. It was completely dark for not just 1 week, but weeks and into months.
So Project OWL is kind of a 2-part solution. We have a software incident management system that first responders and civilians can use to manage a disaster, coordinate resources, learn about weather patterns, and get information data analytics through the cloud.
For the hardware aspect, we leverage IBM's IoT platform, the cloud and database, Node-RED.
The hardware component allows us to distribute OWL incident management software to the worst disasters where infrastructure and connectivity might be offline.
Once this network is deployed, this network of ducts are deployed in a cluster or cluster duct, the civilians are able to basically get on the devices, to a really intuitive interface, contact the responders, and basically send a list of things that are really essential to them.
You walk into Starbucks and you want to connect to the Wi-Fi, a little page comes up, so it's kind of the same idea.
This type of efficiency can dramatically impact how many people can be saved during a disaster.
Yeah, so if you noticed, right, they had a very full-fledged solution where they even thought about the hardware piece of it, right? So they are literally small rubber ducks that can float around, even if it's a flood-ridden area, and each of them is connected to an IoT device, IoT-enabled device, creating an artificial mesh-based network. And anyone who's stuck over there can connect to that network and send out SOS calls or ask for help or ask for food or whatever it may be. So this is one example. There are multiple. I just play one more if I can. So another one which is closer in Nepal, right, is related to earthquakes. And one of the problems post the earthquake is in terms of figuring out.
I get a lot of questions about programming, but I don't think they're the right questions to ask. Questions like, how many languages do I need to learn? What language do I need to learn to get to company X? What's the difference between...
Sorry.
When an earthquake strikes, two things can happen. A house can be completely damaged or it can be partially damaged. PD3R stands for Post-Disaster Rapid Response Retrofit. What PD3R wants to do is to assess those houses that can be fixed or strengthened, and doing that in a very quick way using artificial intelligence.
We worked with artificial intelligence solutions. We dealt with the data that was provided by the rest of our team members. We used the IBM Watson engine, the visual recognition engine, to train our classifier. We also use the Watson API to build a mobile application where homeowners can upload those images and then the classifier would be deployed.
Where I come from, Nepal, it's very vulnerable to earthquakes. My family was affected and they experienced this earthquake and multiple aftershocks, which was a very traumatic experience. Because of this, everybody over there live in constant fear of how our country would be able to respond to the next big disaster.
I believe Call for Code is a very good opportunity to scale things up and to scale good ideas.
We deploy dynamic artificial intelligence to be able to offer free structural engineering advice in disaster-prone regions and be able to ultimately save lives after disasters.
Okay. So if you saw two different examples, right? One of them leveraging a lot on IoT, and the other one leveraging on, things like artificial intelligence, visual recognition, so on and so forth. So, and several other examples, right? So this was a really, a very different exercise where we saw some of these technologies being used in relevant areas and real solutions that can be deployed. Another piece of data or technology that we've very effectively used closer here in the country is the weather data, right? So the Weather Channel data is an IBM company, and we have access to weather data across the world. And when we had the flooding or the heavy monsoon, the heavy rains in Kerala last year, you could see that this was the picture that we created as part of that. A lot of this weather data was available to the disaster relief agency in the state. And it helped the officials prepare better, right, in terms of not just planning, but also planning even post-event. And some of it comes through intelligent dashboards, control centers, so on and so forth. So amalgamation of all these technologies, we've also started on something known as Code for Response. So a lot of these solutions that came out from the work last year are currently being deployed. So we've started with Puerto Rico. So the Project OWL is currently being done in Puerto Rico. And they work with the IBM volunteers to go ahead and do that. So I will pause here. This is the challenge for this year, and we are really looking at a whole set of agencies and organizations joining hands to really embark on the journey of getting developers to come together and build solutions that matter. Thank you.
Thank you very much, Seema. The music was very good. And so were the two examples. I particularly liked and quite intrigued by PD3R. We still have a large reconstruction program going on in Nepal. It would be interesting to discuss more in depth how we can use that to support housing recovery. With that, Sela Nevo from Google, they are doing some fascinating work on flood forecasting using artificial intelligence, and they have piloted it in some parts of India. So,
hi everyone, my name is Sela. I lead the Google Flood Forecasting Initiative. And first I want to say it's an honor to be here and to speak in between all of the amazing work that's been presented here throughout this conference. But before we dive into that, I want to make a general note. And say we believe that artificial intelligence and machine learning-based solutions have the potential of being incredibly valuable for humanity as a whole. But to achieve that promise, we need to make sure that governments, private corporations, and NGOs work together, to utilize this important abilities to improve the world, but also to do so responsibly and make sure that we indeed use these technologies for social good. A few examples of these include our diabetic retinopathy project. This is work that's been, research that's been done in Google for several years now, and we've recently launched within India our first pilot diagnosing diabetic retinopathy in individuals, which in addition to being more accurate than trained professionals, it is much more scalable, which allows us to provide the service in rural areas and underserved areas where that expertise just doesn't exist. We've also just last week launched Bolo, which is an app that helps teach children how to read and uses machine learning-based speech-to-text and language understanding to not only be interactive and engaging, but also hear what the children are saying and how they're reading and correct the way in which they read based on their reactions. But today I want to focus on the flood forecasting work that we've recently piloted in India. As many of you know, flooding has immense impacts. It affects hundreds of millions of people every year, including thousands of fatalities and billions of dollars in economic damages. But on a more optimistic note, it is also one of the natural disasters who much of its harms are the most preventable. It is estimated that up to 35% of economic damages and up to 43% of fatalities can be prevented through early warning systems. And these facts have led both Google's crisis response teams and independently the UN's natural disaster report to assess that flood forecasting early warning systems are a potentially high value and low hanging fruit intervention, which has led us to open the Google Flood Forecasting Initiative, whose goal is to provide scalable, high accuracy, high resolution flood forecasts and warnings globally. We believe that for people to be safe and informed everywhere around the world, we have to use systems that are both computationally scalable and financially sustainable so that we can launch them anywhere rather than only in unique places that can afford it. It's also worth mentioning that our goal in this project is not to make sure that Google provides these alerts, but to facilitate the creation of these systems. We're committed to making all of our forecasts and alerts publicly available, open sourcing as much as we can of our data, and supporting the larger ecosystem to improve both forecasting and mitigation efforts. So why is Google involved in this at all? We believe that Google has a lot of resources that can help move the needle on this important challenge. Google has public-facing interfaces in the hands of billions of people around the world. Those can be utilized to notify people of emergency information in real time. These models require immense amounts of computational resources that are not sufficiently allocated today. And perhaps most importantly, we believe that machine learning expertise can really make a revolutionary change in the way in which we run these models and the accuracy they can have. And in a moment, I'll talk a bit more about that. But we also recognize that Google is in an assistive role in this field. Governments both have the infrastructure and the mandate to protect their citizens, and there are many organizations, many of them sitting here in this room, that have the expertise in these fields and have been doing this important work for many years, many of them even before Google was founded. We want to be able to help with the resources that we can uniquely provide, but do this to create collaborative, innovative solutions that take into account the full ecosystem. What I want to focus on today is our first effort, creating a global, scalable hydraulic model. Hydraulic models are meant to simulate how water will behave when it moves across the floodplain. This allows us, as we can see here on the screen, to know exactly what areas are going to be affected, and therefore who needs to be warned and where they need to go to be safe. Let's start with a broad overview of what this project looks like and then dive into a bit of the details. First, we collect satellite imagery from multiple sources. And from the satellite imagery, we produce high-resolution elevation maps so we know what the topography of the ground looks like. In parallel, we collaborate with governments, and we've started with the Central Water Commission and the Ministry of Water Resources here in India, and receive from them the gauge measurements and the river gauge measurements and forecasts for what the water level is and will be in the near future. We can plug those two inputs into a hydraulic model. This model is what tells us exactly where the water is going to end up by the end of the flood. And this produces an inundation map that we can then use to alert people. It's worth mentioning that these efforts are currently focused on riverine floods as opposed to flash floods and coastal floods, which are also immensely important, but not our focus at the moment. Now, there are several challenges to generating scalable hydraulic models. Perhaps the most important challenge is the scarcity of elevation data. In the majority of the world, the resolution of these elevation maps is fairly low. For example, the industry standard today is SRTM, which is about 90-meter resolution. What you're looking at on the screen right now, on the right, is a high-resolution simulation of a river, first being filled with a normal amount of water, and then overflowing as we pump into the model larger amounts of discharge. On the left, you can see that same river with the same amount of water, but modeled based on SRTM at a 90-meter resolution. The problem, at least in this instance, is that the elevation map is so coarse that we miss the necessary features to model the behavior of water inside the river and outside of it, which leads to the result that in many areas, running these models is effectively useless because the river seems to be overflowing everywhere, no matter what the state of the water inside it is. Another challenge is the staleness of these elevation maps. So SRTM that I just mentioned is an invaluable resource, but it's also almost 20 years old. And the problem is that many rivers, especially those that suffer from severe flooding, change quite frequently. We can see two examples here on the screen. And to be able to forecast the next flood, we need to know what the topography is right now and not what it was years ago. Part of the reason these maps globally are coarse and usually not up to date is because the standard way of generating them is through specialized satellite missions and hardware. One example of that is using stereographic imagery. You send either a plane or a satellite with multiple cameras. Those cameras take images of the same location at the same time, but from different angles, and through the difference in those angles, you can identify what the height of the ground is at every single point. We're taking a slightly different approach. Instead of using specialized hardware, we collect large amounts of high-resolution optical imagery that is already being taken every day around the world. We then combine that information to try to estimate the elevation maps. Specifically, what we do is very similar to stereographic imagery. We look at the different angles at which those images were taken and try to estimate from that the elevation. But the difference is that instead of relying on specialized hardware, we use these relatively arbitrary images. Because these images were not taken with this goal in mind, this means we have to work a lot harder on the software side. This means we try to estimate simultaneously both where the cameras are pointing and what was their exact angle, what is the surface geometry, and various other aspects of ground reflectance. However, once we have this software established, we can then create 1 meter resolution elevation maps anywhere in the world and scale this up to update it, at least where necessary, every year. This allows us to move from the resolution that we see on the left. I don't know how the screen doesn't allow for the full impact of the change, but on the left, where we have 90 meter resolution maps, to an image you can see on the right, where you can identify things like buildings, trees, canals. But the map on the right is still not exactly what we need to produce, to use for our models. Because the map on the right is what's often called a digital surface model. It includes things like buildings, trees, bridges. And that is a bit problematic, because if we simply use a map with bridges and trees on it, our models will assume that those bridges are dams, right? It doesn't know exactly what's happening underneath them. And that will obviously lead to very terrible modeling results. What instead we need is a map that can ignore structures that the water can flow under, but still continue to retain structures that block the water's progression. To do this, we use convolutional neural networks, what kind of is commonly referred to as deep learning, or one of the things that is commonly referred to as deep learning. These allows us to automatically identify what structures we want to ignore and then remove them from the map, as you can see here. So you can see a lot of buildings there on the right, for example, which are just easily removed, and we found this reaches very good accuracy results, even using relatively simple and what we call shallow, even convolutional neural networks. But elevation maps are not the only challenge. Another important challenge is the computational costs. As we want to scale this globally, obviously the number of CPUs we need to use increases. And even worse than the scale at which it increases as we increase our coverage is the scale at which the computational cost increases as we try to increase the resolution. One interesting characteristic of these models, or at least of the classical hydraulic models, is that the computational cost, the number of computers you need to run these models, rises as the cube of the resolution you use. What this means is, if we've now increased the resolution 90 times, from 90 meter to 1 meter, we will need 700,000 times the number of computers to run that same simulation on the same area. And this very quickly becomes unsustainable, even for Google, but even more so if we eventually want to provide tools that every government or NGO will be able to use themselves, which is what we hope to achieve. To do this, we're also trying to use machine learning to scale up the efficiency of these models, as this very self-explanatory slide shows. So what this slide is trying to say, other than look how smart we are, is broadly the following. We train our neural networks based on the physical equations. So we use the classic physical equations that we use for modeling directly in the past. We now use them during our training stage to teach our models what is the behavior of water on the ground. We can then use these models, which are substantially more efficient, to then actually in real time provide the analysis for each location. What this means is we work hard once in limited locations, but then can scale that up globally and do interesting things in real time. But of course, the reason we're doing this is not just for the lab simulations. The reason we are all here is so that we can provide people with information, and keep people safe. To do this, we have three main strategies. First, we're using Google's public alerts infrastructure, which allows notifying people in real time of emergency messages through Google Search, Google Maps, and Android. This system has already provided hundreds of thousands of alerts to over 2 billion people, and we're now fitting it to be able to provide the additional information, the richer and more accurate information that we can now produce. The second way in which we're using this information is to directly inform the governments we're working with. We've begun an amazing collaboration with the Central Water Commission, who are also here in this room, so that we can provide them with much richer information than the little amount of information that individuals have to deal with. We can give them multiple layers that can inform them on timelines, as well as different risk aspects of what's going to happen. It's worth mentioning, we think this is an incredibly important part of what we do with this information. Governments are the ones who can provide a lot of help in the short term through relief and mitigation efforts, but also, as was already discussed this morning, a lot of improvements to people's safety in the long term through infrastructure work such as building dams and embankments. And then our third strategy for utilizing this information is outsourcing these alerts. We recognize that many of the people who need this information don't have access to the internet. And while we think Google is perhaps very well placed to inform people who are connected to the internet, we don't think we're well placed to inform people who are not. That's why we're providing this information to local NGOs to distribute this to the community in offline ways, in a whole long list of creative methodologies that they've developed. We then also fund these organizations through Google.org to make sure that they have the resources necessary to be effective. In general, we try to make all of our alerts publicly available in both human and computer-readable formats. We want any government, organization, or company to be able to use them in any way they like. We want them to either just directly use them to inform people we don't reach, or build upon them with additional information layers, trying to assess vulnerability, for example, or indirect effects, and perhaps use them in ways that we just haven't imagined yet. We've launched our first pilot of the system in Patna in the monsoon season of 2018. What you're seeing on the screen right now is an example of an alert we sent out specifically in September 9th, 2018, and ended up being a good representation of the situation on the ground. These alerts ended up, on average, achieving over 90% accuracy across our key metrics. And we're very encouraged by these good early results. But most of the work is still ahead of us. We're working mainly in two separate vectors. One, scaling up the systems that we already have. In this monsoon season, we're working to scale up within the Ganges and Brahmaputra, but eventually we want to cover India and achieve global coverage. Simultaneously, we're also trying to improve the forecasts that we provide. We have several different efforts that we hope will A, increase the lead time so people can have more time to prepare and protect themselves. Secondly, improve our communication structure to make sure we manage to provide people with as much information as we can and are effective at encouraging them to take protective measures, such as evacuation when that is relevant. And thirdly, try to support new drivers of floods and new ground conditions that we don't yet support. For example, the coastal and flash floods that I mentioned before. We believe this project is a great example of how governments and private companies can collaborate, and we believe that this kind of collaboration can lead to a lot of good, helping many people. We're very interested in similar collaborations with governments around the world. Thank you very, very much for listening.
Thank you very much, Sela. That was fascinating, particularly those equations. And a lot of promise. We would, look at how the system performs in 2019 floods as well as you expand beyond Patna. And then ultimately, from the perspective of the subject of this workshop, we would like to link it to the performance of infrastructure as well, infrastructure that is designed specifically for flood control. There may be very interesting opportunities to explore. With that, let's now hear Andre Cuomo. He has something very interesting to talk about in terms of monitoring in real time the health of infrastructure.
Thank you, and thanks to everyone. We started this project in 2012, starting by chance, really, and then progressively moving from designing sensors to a full system. What is the objective? The objective is to create an affordable, first of all. So we are talking about full costs of some per thousandth per year of the cost of building an infrastructure. A reliable real-time monitoring and diagnostic civil engineering industry able to really give a real-time status of any structure. I will go quick. There are many reasons, from variations in the applied loads. Yesterday somebody was talking about coding, but codes are changing all the time also because loads are changing. Of course, aging, of course, maintenance, of course, issues are construction defects, and there are also extreme events, as we've been talking all these times. So what do? We study the structure and create mathematical models. Then we analyze images taken from any source. There are satellite systems that can see movements of 1 millimeter every month. And of course, we process text and drawings. We integrate data sources. We optimize at this point the monitoring system, so what to monitor, where to insert sensors, and how to get the right information at the right place. And then we automate modeling, and we install the system. We measure variables, tilt, acceleration, stress, displacement, sound. We send the data, we collect the data, send the data to the cloud, create digital twins, which means we update the model we have. So at this point, we have a virtual copy of the original system. And then we discover anomalies, we compute residual asset lifetime, and we optimize the cost of ownership. We have two models, fundamentally, customers who have new structure or a mix of non-critical structures and properly built, and customers who have either old assets or have assets that have not been properly built. So one is risk-based, the other is clearly maintenance-based. We are developing with IBM a civil engineering advisor, so a machine that will help get through the data we collect. And we will have two different roadmaps. One is a civil engineering maintenance application, so trying to go asset by asset. By asset, I mean every element of a structure. And the other one is a risk profiling, basically saying which structures need intervention where, which are urgent, which can stay. We have some cases here. This is a bridge installation we made. Basically, we've been able to see single strands and then the whole cable breaking. But we have also been able to see real-time traffic. You can see easily the difference on this slide between weekend and heavy traffic. We have seen earthquakes coming. We've seen the behavior of the structure during the earthquake, before, during, and after. And we've been able to conclude fundamentally in real time that no damage has occurred on the bridge. We have seen this, for instance, this monitoring is going, and diagnostics is going on since 2.5 years with a few thousand sensors. It's a tunnel in the middle of a landslide, and we've been able to see the deformation, but not only the shape. We've been able to compute the force that the mountain is exercising on the structure, the bending moment inside the lining, and of course project this force for 40 years and beyond, assuming the landslide doesn't change in the middle, but this is the best assumption you can make today, and then come to a conclusion and say when we expect that structure will no longer be usable. So basically when a fundamental repair need to take place. We are doing the same work on bridges. We are equipping bridges with sensors. We are, of course, after having designed the monitoring system, verified, etc., updating the model and doing some load tests to trim and finding out the difference between the theoretical model and the reality of the bridge. And of course, we have world-class partners on hardware, on software and cloud, people like IBM or Gavious, the fourth largest highway operator in the world. Sundbyberg owns the big bridges between Sweden, Denmark, and the continent. ST, who's making materials. The idea is to scale. Where are we today? Today we're equipping fundamentally one bridge per week. We need to do it one bridge per day by the end of the year and being able to deploy this system. What is the business model? Of course, this is a heavy civil engineering work. Technology is a service. We're not changing the world. It's people who apply technology who are changing the world. So we will provide technology to partners who, in different areas of the work, will be able to do the engineering work needed to support the technology. I want to say it again, we are providing the full service, including real-time data, because we are connected to the cloud, including access to the result, including reports, diagnostics, and whatever. We're able to do it on, at a cost which is in the some percent of the cost of construction. So it's many countries is well below, in most countries, well below the yearly inflation. And this is where we are doing. So the point, what we are really doing is what is the status of an asset, how urgent an intervention is needed, how can you build a reliable priority list. How do we do it? We analyze the structure, we build the mathematical models, we design an ad hoc monitoring system. We don't place sensors here and there, not knowing what we do. We update the model with real data, and then we compute the residual asset lifetime project over the year. It's a scientific-based computation. The partners in civil engineering have been chair of the International Concrete Federation, chair of the Eurocodes, Fressinet Medal, for those who know what it is, basically some of the most important civil engineers in the world. It's real time. Data can be sent are sent to the cloud anytime. We can decide, and the user can decide how many data will stay in the gateway and how many go back to the cloud, not to clog the cloud with useful information, but getting everything you need at the right time when there is an earthquake or an event or when you need them. It's connected to asset management tools to optimize maintenance and to risk management tools to generate alarms. And finally, we believe we are in the cost structure of making it affordable at high volumes across the globe. Thank you very much.
Thank you, Andre. That was a very, very interesting presentation. We, in our own country, have a huge problem of old bridges. You know, every, a few months you hear the collapse of a bridge. So, it would be interesting to explore how this technology can be used, what business model would apply. So I think this is something which perhaps requires more detailed discussions bilaterally with you to understand it a bit more.
I forgot to add one thing. It can be applied, of course, to top of the tunnels, to landslides.
Yeah.
We are applying to buildings. We are applying to dams. I didn't go through for the 10 minutes.
Yeah, many different kinds
can
of
go
structures,
across the board.
Yeah.
And also landslides.
Yeah.
You can see inside the ground how the landslide is moving.
Thank you for that. So now I turn over to Michael Anthony.
Thank you very much, Mr. Kishore. Thank you for having me. It's a great pleasure and honor to address you and give you a bit of a short glimpse from space. That's really what I'd like to do, and I'll keep up to the Swiss paradigm of punctuality and keep it to the 8 minutes so we can make good some time. I probably logically follow up a bit from the previous speaker in some of these assessments that we're doing. We're basically a small southern Switzerland-based company that is focusing on the interpretation of satellite data, and a particular kind of satellite data, which I'll move on to explain. We recently also set up an affiliate here with Indian partners in Mumbai, based out of BKC, and we're called Earth Analytics India here in India. And really what we're focusing on is the interpretation of radar-based satellite data. Now, radar-based satellite data, which is basically a different spectrum, is useful in two occasions. One, it can see through the clouds. That is very important when monitoring agriculture, so that is very important in this country, where agriculture plays such a large role. But whenever you use satellite data to monitor agriculture, the only thing you see in the main season are clouds, which is not particularly helpful. So radar sensors can permeate the clouds. The other application, which is relevant to the discussion at this plenum, is to use it to measure stability of infrastructure. And I'll give you some examples as we move through from India and also beyond. And this is actually the map of Mumbai. We are computing an infrastructure stability index of Mumbai. You see this is a fairly coarse resolution, so 1 pixel is 30 meters. But you can still probably recognize, at least those of you familiar with Mumbai, the geography of the city. It's projected on a Google map. So you will see on the bottom left corner actually the Worli Sea Link, and since Mr. Kumar was worried about the stability of bridges, I can assure you it's all green, it's all stable, so nothing to worry about the Sea Link. Obviously that was something that we also looked into, but you can see by the color coding on the top right that there are some elements where there's either a subsidence or an uplift of the ground, potentially a piece of infrastructure or the ground that we observe. And we observe this by measuring the distance between the satellite and the object on the ground. Now, the satellite, and this is being done through the reflectance that the waves of the radar sensor are emitting and that are being reflected back to the satellite. Now, the satellite moves around every 6 to 12 days, depending on which constellation is being used. So every 6 to 12 days, we are getting the measurement between the satellite and the object on the ground. And by that, we can see if the object on the ground is sinking or is moving upward. It's basically the same technology as being used, by the way, in speed control, radar-based speed control in Europe or other countries. So we looked at Mumbai Airport, for that matter. Those of you flying in and out of Mumbai might have noticed that since November, the airport is being closed for maintenance work between, I think, around 11 a.m. and 5 p.m., so there are no flights going from Mumbai. So we had a look at the airport, and we found that, in fact, yes, there is, excuse me, subsidence going on around the runways. So we observed Mumbai Airport, or we got the data from Mumbai Airport, satellite data over the last 2 years, and we found that over the last 2 years, actually, the ground on and around the runway at some points is of several millimeters per year. Now, that was very coarse resolution, so it was a precise measurement of the millimeters, but it's a coarse resolution per pixel. We talked about resolution earlier on, or the seller from Google was mentioning that. Now, some of the satellites have higher resolution per pixel, so if you want to analyze a particular important piece of infrastructure where higher precision is needed, then of course one would have to resort to higher resolution data. So here's an example of train tracks. There's going to be a panel in the afternoon also with some Swiss contribution on train tracks or trains, and as an important piece of infrastructure. And here this is the French example. The French have a huge high-speed train network crisscrossing France, and of course their prime concern is to ensure that it's being safe. And in fact, there hasn't been any accident, and it's also because these train tracks are thoroughly controlled, and among other things, using satellite data. So in this case, the exercise was being done by Airbus, which is a client of ours, and they wanted to know how stable are the area around bridges or hillsides that are encroaching on the train tracks. And what you can see here is marked in red, that there is actually movement of up to 2 centimeters on average per year, where the adjacent hill is putting pressure on the bridge construction and eventually on the railway track. So clearly this is something that the French railway operator wants to monitor and wants to share with its engineers to see how much of stress such a structure can bear, and at which point there needs to be some engineering intervention. Another example are pipelines, water pipelines. So here's an example of central Italy, where a water company was noticing that their water pipelines are frequently breaking, and they wanted to better understand the cause of that, which was not due to the erosion of the actual pipelines, but it was, as we found out, due to deformations and some parts, to an extent also seismic activity in the area through which the pipelines were leading. And again, using this interferometry approach, which I mentioned earlier on, you can see here on the screen that there is a eastward movement when it's marked in red by around 3 centimeters per year, or a westward movement by around the same, in the same scope, putting pressure on the pipeline, and that was actually the cause of the pipelines breaking. And of course that information is important for the water company when they're planning future pipelines, or when they're planning on how to use the pipeline network, where water flows are, what are their contingency plan in operating the pipeline network, because they have an understanding of where there is stress on their infrastructure. And this is then the scientific evaluation that our software would be generating. Coming to this country, we also did some work together with the Swiss Development Corporation that is, of course, very much concerned or has a good understanding of mountain ranges. Switzerland is a very mountainous country, but so is India. We had been looking at the deformations and displacements that the authorities in Sikkim have reported to understand what is the extent of that deformation and how could it potentially be used in an early warning system to derive hotspots and derive those areas that are particularly under stress. Now, you don't always need satellite data. I think here it's pretty clear that the people who are living in this house are facing great risks, and they probably either have a very strong self-confidence or a very strong belief in God that they are still living in this house. And there were other instances that we observed, actually more in a live visit, that infrastructure is in dire straits through these deformations of the mountains in that area. So clearly it is the ex ante information that remote sensing satellite data should bring in, which is relevant. And this is something which I think we will be seeing more and more, because what we can observe in terms of the hardware development is there's almost a Vanity Fair in space. If you look at these different satellite missions that have come up over the last couple of years only, and of course they're backed either by countries So you see the flags up there, and on the left one, those are the traditional ones. So the Japanese and the Canadians were into it for quite some time. My previous speaker mentioned the Italian constellation, which is also very developed. Now the European Union and hopefully or potentially India and NASA, Israel and NASA, that are planning a mission to start in the next 2 years, will be free of charge or at low charge. We know that for the European Union, we assume that for India, but we don't know yet. And that, of course, is extremely valuable because it helps that technology to set foot in actual real applications. And we also see commercial applications, particularly funded out of Silicon Valley, but there's also a Finnish constellation that is coming up. So there's going to be a vast amount of data which waits to be translated into, if you like to call it, downstream services and applications. And I think this is something which we're going to see and which we are there to help for. I'll skip my last slide and leave you with my contact details, and thank you very much for your interest.